Here we go. We've got ourselves a problem. It says find the derivative of f of x equals 1 over x. What in the wide world is the derivative? Well, we found the derivative at a point before. The derivative is essentially the function that gives us the slopes of f of x at any point. So instead of having to plug in one value to start, we're going to get a function so that we can plug in multiple x values when we're all done and get the slopes anywhere along here. So that function that we use is very similar to what we've seen in the past. I'm going to use h here. The limit as h goes to 0 of f of x plus h, not c. And the difference there I'll show you on this graph in a second, all over h. Essentially what's happening here is we now have ourselves a point and then another point right here. This point here, x comma f of x, think of that as a point that can be moved anywhere. And think of this as a point that can be moved anywhere. So this function now allows us to not just fix everything here. It's a matter of notation. So before, when I taught you that it was c f of c, that point could not move. Now we can use this function to find the slope anywhere by calling it x comma f of x. It's a matter again of notation. So we're still going to do the process very similar to what we did before. We want the slope essentially of this function at any x value. Well, what we do is we now follow this template. It says take x plus h and plug it into f. Well, f we take 1 over the x value. So that would be 1 over, and of course we need our limit. Can't go anywhere without that. The limit as h goes to 0 of f of x plus h. That'd be 1 over x plus h minus f of x. Oh, this is about to get filthy algebraically. All over h. So that's pretty gross. But the good news is you've evaluated limits like this before. It was all up in the limits chapter. So here we go. One thing that I like to do, I like to use the clear out fraction technique. If you need a review on that, go back to the lesson over limit techniques in chapter 1 and check it out. All right, so anyway, we've got to clear this out. I'm going to multiply numerator and denominator by the common denominator up here. So that'd be x plus h times x. And what I do to the numerator, I'm going to also do to the denominator. So from here on out, just to be very frank, all we're doing is finding a limit. You've done the derivative part. The end result will be a function that is beautiful. So when we multiply by x plus h times x, that gets multiplied here. The x plus h's will cancel, right? Remember, this is getting distributed to both. So x plus h's cancel, leaving you with just an x. So I've got the limit as h goes to 0, it's a pretty terrible arrow, of 1 over x plus h times that, and then your x, again, like I said, is remaining, minus, well, the x's will cancel when they're multiplied, leaving you with just an x plus h in the numerator, all over h times, there's no point in multiplying this out. It's the numerator we needed to kind of toss around there. And again, the reason why we had to do that is if you had plugged in 0, top and bottom, you would have gotten 0 over 0. Let's simplify. Let's find this limit. You know you got this. Let's keep trouncing through this. I don't know, trouncing? I guess that works, right? Let's keep hitting this problem with the algebra baseball bat. So we've got the limit as h goes to 0 of, well, x minus x is 0, and you're left with minus h. That negative comes to that h. All over h times x plus h times x. Where am I getting these terms from today? Let's hit this problem with an algebraic baseball bat. I don't mean that violently at all, but thinking back on that, thinking, man, it's not how I want to go through this problem. Let's gently rock this problem. How about that? So h divided by h, they completely divide out. And we're left with, oh, well, let's see, the limit as h goes to 0 of 1 with a negative, all over x plus h times x. And this is going somewhere fast, because now we can plug in our 0. When we plug in 0 here, we're going to get negative 1 over x times x. Plugged in 0 for h, x plus 0 is x. And that's negative 1 over x squared. So what is that? What is that thing? It's not a number. It's the derivative. That's what that is. So that is your derivative. It's what I like to call the slope generator. Any x value, as long as it's in the domain of this function, if we plug it into this, the number we get out will be the slope of the curve at that point. For instance, we're then asked to find the slope of the tangent line to f of x at x equals 3. No problem. So we'll do f of 3, and I should say f prime of 3. What is that notation? That means the derivative of f at 3. That's what that little thing is, and it's read f prime of 3. Well, that's equal to this. Negative 1 over, plug 3 into it. It's the function that gives you slopes at any x value. And that'd be negative 1/9. And sure enough, if you look at this curve right here at x equals 3, it's got a pretty, well, it's negative slope, but not so steep slope, very gradual. Let's say you wanted to find the derivative or the slope of 1 over x at 1. We write f prime of 1 and we plug 1 into this. You don't have to go through and do a whole nother limit. That's the beauty of this. Negative 1 over 1 squared is equal to, again, plugging into this, negative 1. Sure enough, that's here. That slope is certainly about a slope of negative 1. It's awesome. That's it. That's your slope generator. And again, the notation, if we're finding the derivative of f of x, you could write it as f prime of x. That's the derivative of f of x. And in a later video, I'll go over other ways of notating that. Okay, we got a little bit more in this video, but this was the main part of the attraction. Let's do a little bit more. So I'm going to stick with f of x equals 1 over x. And we're going to find something else, and you're often going to be asked this at about this time in your calculus studies. You'll be asked for the average rate of change. What is that? Well, in this previous graph, we did what is also known as the instantaneous rate of change. That instant, what is the slope at that point in time? The average rate of change is, what is the slope over an entire interval? So if you're driving on a highway for 2 hours and you go 120 miles, the average velocity or speed would be 120 miles divided by the 2 hours you've gone. Rate, right, is distance divided by time in that case. Well, this is what we're doing here. Essentially, we're just being asked for the slope. That's all. So the slope of the secant line. You could think of it that way. And I'll write that out for you. So, and I'm telling you the answer to this, I guess, early. So what is the average rate of change? Well, it's y2 minus y1 over x2 minus x1. You'll often see that written as f of b minus f of a all over b minus a. All that is the exact same thing as rise over run. That's it. So we want to know the average rate of change from 1 to 4. So graphically, I'm going to answer this question next. What does your answer represent on the graph of f of x? Well, if we're going from x equals 1 to x equals 4, we're essentially then finding the slope of the secant line, which would be this right here, the slope of that line. That's all we're going after. Not bad, right? And I'll draw that down a little bit bigger so it lines up. So how do we do that? Well, you could do rise over run of the graph. That works. Or we could be fancy like f of 4. That would be the y value here minus f of 1 all over b minus a, which is that x value of 4 minus the x value of 1. And so if you're looking at it notation-wise, this point is 4 comma f of 4. And this point is 1 comma f of 1. You're just doing y2 minus y1 over x2 minus x1. That's it. Well, how do we find f of 4? From the function. F of x is 1 over whatever the x value is. We want 1 over that x value. So that's 1/4 minus f of 1. 1 over 1, which is just 1. All over 4 minus 1, which is 3. And now from here, we'll simplify. 1/4 minus 1 is negative 3/4 divided by 3. When we divide a fraction by a number, that's the same as doing negative 3/4. You can think of this as 3 over 1 times 1/3. You multiply by the reciprocal. The 3's divide out, and you're left with negative 1/4. And that is the slope of the secant line. It's not the slope of the tangent line to the curve. So this is not the derivative, but it's a pretty darn good approximation of a derivative somewhere around here. And that's how you find average rate of change. So if someone asks you, hey, can you find the average rate of change? You're going to be like, sure. You mean the slope between 2 points? I got this. And you do got this.